Okay, cool. Thank you. Yeah, welcome everyone today to the next iteration of Rocky World's discussion. Before today, we have Xinting Yu from the University of Texas, San Antonio with us. She will give a talk about from Titan to exoplanets, exploring the diversity of rocky worlds. Before I give the stage to her, shortly about our organization. So we'll start with her talk, and then we go into a Q&A about 10 to 20 minutes. Shortly about the netiquette, please use your full name, keep muted while we have the talk. And when you ask a question later on, if possible, if at all possible, please show your video when speaking. Okay, so now I'll stop the slide share and I'll give the stage to Xinting. Take it away, please.
Yeah. Thank you guys for the invitation, but today I'll be talking not directly rocky worlds, but really from other rocky world similar bodies to really explore the diversity of rocky worlds. So I'm going to be talking about Titan, super sub-Neptunes, but these are all worlds I would say have potential to be close to rocky worlds, I would say. So just to give you an outline of what I'm going to be talking about today, I'd like to first talk about some laboratory work we've been doing, the collaborative Haze analog study in the lab to basically measure different kinds of Haze samples that are produced for Titan's purposes. And then I'm trying to make you convince you that this kind of study will be beneficial for not only Titan, but to study hazes and astrobiology and other bodies as well. In the second part of my talk, I'm going to be talking to you about how do we find the appropriate surface conditions on sub-Neptunes. And this is really to give us a potential to discover more super-Earth-like planets within the current era of space telescope instrumentation we have, which is basically the James Webb Telescope era, the James Webb Space Telescope era. Can we find, before we're able to observe rocky worlds 30 years later with Lucille, can we do something now and maybe discover some cool like super Earth-like planets? All right, and I hope at the end of this talk, you will find out solar system science will be really beneficial for the exoplanet field. All right, to get started, in the next couple of slides, I'm going to try to convince everybody, okay, even though people think, okay, Titan is not a rocky world, it's an icy body, but I will try to convince you Titan might actually be the most Earth-like planetary body in the solar system, okay? So for those of you who don't know Titan, Titan is the largest moon of Saturn. You may argue, okay, Titan is a much smaller body compared to the Earth. It's bigger than the moon, it's actually bigger than our planet Mercury. So that means Titan's gravity is actually a lot smaller than Earth. But then really in the next few slides, you'll see why it's similar. Okay, so the first similarity, I would say the that's probably interests this crowd here is really Titan really has a pretty much Earth-like nitrogen-dominated thick atmosphere. And in fact, Titan is the only moon in the solar system with a substantial atmosphere. So we're talking about maybe 95 to 98% of nitrogen, depending on where you're looking in the atmosphere. And the surface pressure actually 1.5 times the surface pressure of Earth. So it's actually a thicker atmosphere than Earth's atmosphere. But you might be wondering, okay, Earth doesn't look like a giant yellow ball. So what are you looking at here? So actually, if you look from the other angle, from the limb, you can see this big yellow, all these yellow stuff actually the result of these thick photochemically formed haze layers in Titan's atmosphere. So why are we not a giant yellow ball like on Earth? And this is really because even though the majority of the atmosphere is nitrogen, there is one trace species, well, another dominant atmosphere species that's making Titan different than the current Earth's atmosphere. This is because there's about 2 to 5% methane in Titan's atmosphere, depending again on where you look. And then because Titan is exposed in an energy environment, which means it can receive UV photons from the sun, or energetic particles coming from Saturn's magnetosphere, which all start to come and dissociate atmospheric gas molecules. This could really lead to the formation of the initiation of very interesting photochemistry leading to the formation of organic molecules that are very complex. And actually, the Cassini have done measurements, and we found molecules with mass to charge ratios up to like 10,000. So really crazy complex molecules. And these organic molecules could further polymerize and coagulate, and they eventually form particulate level hazes that we see in Titan's current atmosphere. That's making Titan look like a giant yellow ball. But what am I going to argue that even though Titan's atmosphere is similar to Earth's current atmosphere, it's not exactly the same because there's no oxygen, okay? But I want to argue that the current atmosphere is actually very similar to it might be similar to early Earth before life arises. So there's this hypothesis saying early Earth's atmosphere is actually a lot more reducing than the current oxidizing atmosphere. So that means we'll have some reducing gas, possibly like methane, in the atmosphere. And again, because Earth is also exposed in a energetic stellar environment, for example, UV photons or other energy source will hit the atmosphere molecules. So the same thing would happen to make these organic molecules. So, you all probably heard of the Urey-Miller experiment, which kind of explored this possibility of, but this is actually still one of the, I would say, contenders for maybe this is how the Earth's life originated, from the debate about where life arises on Earth. But I would say at least people agree upon that these organic molecules that are produced by photochemistry during the early Earth period could at least provide the initial organic matter for life to brew upon. So it's just some organic matter there, and life can use it to some extent. Either that's how life arises, or maybe there are some other ways, but this is a material that they can use, basically. And there are some other resemblances I like to show people, really, because I think they're super cool. So I used to quiz on people. So this is actually radar images. One is taken on Titan and one is taken on Earth for two lakes, actually, there. And they're really similar in size. And I quiz people which one is a lake on Titan. I'm not going to do that today. So I'm going to show you the answer. So the lake image on the left is actually a lake on Earth, and a lake image on the right is actually a lake on Titan. So these lakes look morphologically very similar. The only way I'm going to be able to tell is there's a man-made road kind of on the left image, which is kind of hard to see probably, but this is the only way I can tell like the difference between the two bodies. But the conditions on these planets actually very different. So Titan is much, much colder than Earth. So water, we all know that Earth's lake is made of water, but on Titan, it's because it's much colder. Water is already in the ice form. So the lake liquids we're talking about here is something else that could actually condense at this temperature, could condense and also be a gas in this temperature. And this 94 Kelvin is actually a magic temperature for methane, because 94 Kelvin is actually very close to the triple point of methane. So Titan actually can have methane as a liquid and a gas. And that's why we see lakes just look like morphologically like the lakes on Earth. And I like to talk about some other resemblances, again, because I think they're super cool. For example, we've seen dunes in Titan's equatorial regions. They look like these long strips that runs tens and hundreds of kilometers. And we think they're very closely resembling the large linear dunes on Earth. I don't get to see them often because they are usually in areas where nobody lives, but this is actually some linear dunes near Namibia. Again, the only way you can tell is like you can see the beach in the far right edge of the picture. But anyways, I would say I'm a planetary material scientist, and my bread and butter is really to study and measure material properties of all these relevant planetary materials inside and outside the solar system. And the point I want to make by bread and butter is like planetary material property really matters for various planetary atmosphere and surface processes. For example, I have found that various planetary material property, for example, we know that the material on Earth and Titan are actually very different. By measuring these different material properties, such as cohesion, electrical property, mechanical property, we know that the way that even though the processes look very similar, like the dunes or the lakes, actually the way they operate is kind of different because of the material property difference. And similar thing for atmosphere processes such as cloud formation or haze growth, stuff like that. But today I like to draw your attention to people because this is a Rocky Wars discussion. I like to say that the resemblance between Titan and the Earth, one of the most important that can inform on future Rocky Wars studies really is haze formation, how the haze can provide maybe the initial organic matter for life. And that really has lots of implication for exoplanets. For example, if we found a reducing atmosphere for Rocky Wars, we might want to evaluate in the lab, okay, what kind of organic molecules could be made by atmospheric chemistry, and could this planet potentially have the potential to lead to more organic life matter formation, and then may lead to life forming maybe in the future. All right, so I've been studying haze in the lab for many years, but to date, we actually do not have samples from Titan. So there's no haze sample from Titan. Now, of course, there's no like haze samples from the early Earth period, because that's all like erased by the geologic time scales that we have from now to early Earth. So how do we even study hazes, I would say, in the lab? And laboratory people are actually quite smart. So even though we can't get the samples directly, we can actually mimic the environment that these materials are made in the laboratory. So basically, you want to start with a gas mixture that mimics whatever environment you think these atmospheres would be like. For example, for the case of Titan, we will usually use a mixture with nitrogen, mostly nitrogen, and a few percent of methane as in the gas mixture. And then we will expose this gas mixture to some energy environment. For example, we can use energy sources such as UV lamp to simulate UV photons from the sun, or we can use some other energy sources, so-called cold plasma, to simulate energetic particles. But in the end, you let this reaction go on, you let the gas mixture being exposed to the energy source, and you make this final material, which was, I would say, invented by actually Carl Sagan and his colleague Bishop Carey. And they decided to name this material Tholin because it looks kind of muddy-ish, and Tholin kind of means muddy in Greek, and which kind of describe exactly the experience when you deal with Tholin in the lab. But as I said, I've been studying this material for many years. When I was a grad student, I did this in one lab where my PhD advisor was. But when I finished grad school, and went to postdoc, I realized, okay, it's not just one lab that can make Tholin. There are many labs that can make Tholin. And it seems like everybody kind of been doing different things. So my question was actually, even just for Titan, are these Tholins people make in the lab, are they actually equal to the real hazes on Titan? Because when we write our papers, we claim Tholins are just like the real hazes on Titan. But then that became a question for me. So I did some digging. So I looked at some laboratories that produces Tholin, kind of some of the dominant ones currently in the US. And I just write down the experimental condition that makes, that they use to make these materials. And as you might already notice, if you look at some experimental conditions, you can see variations that span across multiple orders of magnitude. So really, people are using very different methods to make them, and then claiming, okay, these are the real hazes on Titan. I'm not saying this is bad, but I'm just thinking back, okay, maybe we should evaluate more if that is the case. And we should claim that maybe we shouldn't claim all of the lab-made ones are real hazes, or at least examine if that's actually the case. So the approach I decided to go with is, how about we gather all the samples from everybody, and then we measure them and in a standardized approach. So we can really figure out, okay, which kind of experimental conditions and which kind of setup would make Tholin that closely or closer mimic the actual hazes on Titan. So I actually started this effort through a funded Cassini data analysis program by NASA. And the way we do this is basically each of the lab first make their sample, okay? And this is the only different part of this whole comparative study. This is because after the samples are made, they are all transported through a standardized approach. which means we actually develop some standard transportation vessels in the lab. So there's some vacuum. So on top is a vacuum holder we developed, and then on the bottom is a dry nitrogen holder. So this is to ensure after the samples are made, they never touches Earth's air. As if you can remember, the gas mixture that used to make these samples are nitrogen and methane, and there's no oxygen involved. So we don't really want to introduce the oxygen or the water vapor in Earth's atmosphere to really kind of contaminate or modify the samples. And then they'll be transported in a standard way to my lab. This is actually me using a self-built instrument when I was a postdoc at UC Santa Cruz, but currently this is just already arrived at my new institution at UT San Antonio. But we do what we call the standard characterization in Earth atmosphere. Again, the sample never touches the air, and they are all measured by the same instrument and reduce all in a standardized pipeline. So we're only really looking at the sample difference, okay? So we've been doing some pilot study. We actually found to do quite a few material properties of all these samples. So what we found is, okay, there are some similarities, but there are also differences between all these tholins produced from different labs. The first pilot study that was just published last year. Last year we done, actually the first one we done is comparing the surface energy of all these tholin samples. So if you don't know surface energy super well, it's actually a material property that describes the cohesiveness of the material. So if you get a higher surface energy material, it means it's stickier. For example, if you use like Teflon, like airplane, they tend to use like not sticky material, which means they will have low surface energy. And you can also separate the surface energy into two components, a dispersive component and a polar component. So that tells you some information about the bulk chemical composition of the material. For example, if you have like a larger polar component, it tells you this material probably has higher like polar bonds, like higher density of polar bonds in the structure. But we measure surface energy, and here I'm showing the result. So basically what we found that it seems like there are some differences, as you can see, especially for the polar components. But what we found is that seems like the material that's made with the same energy source, among all these different parameters, experimental parameter that goes into make this sample seems to have a larger impact on the final surface energy of the material. So that's really important. For example, if the only way the Tholin's property is controlled mainly by the energy source, maybe we don't have to worry so much about all the other different parameters. But this is just for surface energy. And the second thing we found from this study is really we provided not one number with standard deviations, but a range of numbers that people should really consider in their future modeling work before we figure out which samples actually more closely mimic the actual hazes on Titan. And last thing is, okay, there are some differences, but we also found some similarity across all these samples, which is they somehow, despite the different ways they're made, they all seem to have a pretty high dispersive component of the surface energy. So really the idea is once we identify this kind of common property among all these Tholin samples, we should be more confident to use this common property for our models to really claim, okay, this common property will likely also be possessed by the actual hazes on Titan, because however you made it, this is a property you get. So that's kind of the idea behind this pilot study, is really we want to find the differences and then also find the commonalities, and we should be more confident to use the commonality of the samples in our future modeling or assessment of different processes on the planets. And because I'm now a faculty member at UT San Antonio, which means I have startup money, and I'm actually building a new planetary material characterization facility at UT San Antonio, which are able to measure a range of material properties. My lab is mostly focusing on physical properties, but I'm open to be measuring some chemistry or composition of these materials in the future as well. But my lab is going to be most equipped to do mechanical properties, optical properties, surface cohesion, and electrical properties through all these different instrumentation. And I would say the uniqueness of all my instrumentation compared to, say, like a regular material characterization lab is that all my instruments will be housed in a dry nitrogen environment. So that means all the materials, they never have to touch Earth's atmosphere. So we really don't introduce any contamination or alteration for the properties, and especially some of the properties are very sensitive to the top surface layer. And once you expose these materials in the atmosphere, you get water absorption, and everything could happen to the surface of the sample that alters it. And so it's no longer what it was. All right, so we've done some pilot study. Again, these are not published materials, so please do not distribute it. But we've done some pilot study on measuring the mechanical properties, and we found, okay, these samples are different. So for example, their elastic modulus, we measure them to be around 10 to 30 gigapascal, depending on the samples. But they're also, I would say, similar enough. So we're still talking about elastic modulus for polymer-like materials. So 10 gigapascal, you'll be thinking something like your tire, like for your car. And then 30 gigapascal, we'll probably be thinking about some like very highly engineered polymer. So like that's harder. But again, they're still in the ballpark. They're not entering, okay, the elastic modulus of like metal. So that gives us some confidence, okay, this material still behaves like in a kind of control sense, even though there's some variations. We also measure some optical properties of these materials. So the optical constants N and K, from the UV to the mid-IR, from 190 nanometers all the way to 30 microns. But again, there are some similarities and differences. As you can see, even though there are some qualities, so there's some separation between the two lines for the two samples. So we so far only measured the samples made by cold plasma. You can see lots of the peak actually corresponds really well with each other for the two samples at least. And the main differences I would say is between 5 to 10 microns for these two samples for N. But lots of the peak actually in the same position. And for the absorption K, you can see again, lots of the peaks actually corresponds with each other really well. And the big difference, it seems to be in the like mid-infrared region. So again, from 5 to 10, and also there's a peak of absorption for one of the NASA samples, actually at 25 microns, and it doesn't really appear for the tissue sample. So that means there are some differences for the samples, but again, also some similarities. But really, we like to collaborate furthermore using this approach to study hazes for Titan. But we also want to expand to more planets, including exoplanets. For example, and for Titan, really the idea is we want to measure these material properties. And the reason we choose these specific properties really to, because these properties actually were somehow measurable, already measured by the previous missions, such as Cassini, or in the future by Dragonfly. So that means we can access some of the properties of the real hazes on Titan. And then we can really compare, okay, which of the setups or which kind of experimental conditions make samples that are closely or closer mimic the actual haze samples on Titan. And after we've done this for Titan, we really want to expand it to other planets. But before we do that, I really want to kind of introduce you to my recent paper that's almost out there. But we actually, in the past few years, have been developing a material property database for Titan. But again, all these comparative study results will be dumped to this database. And we actually have a website, a paper, and we've dumped the database kind of everywhere. We're going to do it on PDS and NASA's AHEAD database. But everything will be out there for you to use. I've seen your models, observational calculations. And all these properties are kind of available so far on our current website. And this is through generations of undergraduate students that's working with me when I was at postdoc at Santa Cruz. But really, we really want to expand this kind of collaborative approach to study Titan hazes, and then we want to expand to exoplanets. And we want to not only be doing the physical property measurement, but also composition and other chemistry that could be useful for exoplanet purposes. But really, the things that can be provided from this collaborative study is really, it can tell us better, like help us understand better how the atmospheric chemistry operates. For example, it seems like from our current study, the energy source is really making a huge difference on which kind of sample or which property you'll get. But really want to figure out the key parameter that matters for atmospheric chemistry and the final material it gets. And the second thing, we're going to get more robust database. So we're going to get more like a range of numbers, again, reasonable to be used. And the common property is going to help us understand, okay, these are the properties that you should be more confident in using or interpreting your data you get for especially exoplanet part. But yeah, this is kind of my laboratory part, and really want to tell you kind of how this collaborative Haze study will be beneficial for not only on Titan, but future other planets in the solar system and beyond. All right, the next thing I want to talk about really is something different. So I've been studying like solar system stuff for like a while, since like grad school. And like people who study solar system planets, for example, I study dunes on Titan for my PhD thesis. Every time you run into like a question for like a dune on Titan, you look at the Earth's literature because Earth is a reference point, okay? So all the solar system scientists, whenever they encounter some questions, see some new features on these different planets, we'll first look at, okay, is there something similar on Earth? Okay, so that's kind of the way how the science operates for planetary scientists who study solar system bodies. But for exoplanet scientists, I would say the focus is more from the like formation perspective, also people because they come from the astronomy background. But I'm a person who came from planetary science background to study exoplanets. So my perspective is, okay, can we use the same philosophy to study exoplanets? If we have a question about some exoplanet or some processing on the exoplanet, we not only have Earth to consult to, but all these solar system planets, because we know them far better than most of the exoplanets we have out there. So that leads actually to one of the biggest questions I had when I was when I started my postdoc to study exoplanets a few years ago. Really, I found it really weird that if we've been discovering so many exoplanets, but somehow the most abundant type of exoplanet, as shown in the plot on the left, if you draw like a planet size and their distribution based on the current exoplanet, I found that the most abundant type of exoplanet actually they have sizes kind of in between the terrestrial planets and the giant planets. And really, we don't really have this kind of planets inside the solar system. So there has been, I would say, some debate between kind of the nature of these intermediate sized exoplanets. And I would say that's really a key problem I hope the James Webb Telescope is going to give us some insight about. So people have been arguing, okay, maybe these planets are closer to like either closer to super Earth-like, so terrestrial kind of planet, or they're closer to the so-called mini Neptune, so like giant planet-like, and there will be nothing in between. And some people say, okay, these planets maybe actually belong to like a long continuum of planets. So you'll get like a variety of planets, but these planets just kind of on their own. They're different than terrestrial planets and giant planets, but they're more like something in between. But really, I think one of the ways to figure out which planet is what is how about we kind of find out how thick their atmosphere is, and then what is the surface condition. So I'm saying that because we know the difference between the terrestrial planets and the giant planets in the solar system is that we know the terrestrial planets all tend to have pretty thin atmosphere sitting upon like a surface I call shallow, which means it's closer to the top of the atmosphere. And so we're talking about surface pressure less than 100 bar, with the edge case being Venus here for terrestrial planets. While for the giant planets, we're talking about they don't, if you want to see a surface of some sense, you have to go at least 1,000 bar and above to see some phase transition boundary for these giant planets. But they have very thick atmosphere in general. But okay, if we figure out for these intermediate sized planets where their surface are located and how thick their atmosphere is, we might be able to distinguish what kind of planets these planets are. Are they super Earth-like or maybe Neptune-like, again, or something in between? Well, but if we look at upcoming observations, you'll find, okay, this is going to be immensely hard to do with the upcoming data we're going to have. So for the transit technique, which is really the hottest thing in the exoplanet field, is really great at looking at the atmosphere composition of exoplanets, looking at all these molecular absorption features, but it's really not sensitive to the surface at all. Usually I study hazes, so at lots of time you actually get hazes that blocks your signal. and make your like atmosphere detection even worse. So that means you're getting signal further away from the surface. And the direct imaging technique, which is very, very promising because it is indeed sensitive to the surface condition. But currently we're at the stage we're still seeing very, very big planets through that direct imaging technique. Out of the, I don't know how many, 5 that are detected, most of them are like Jupiter or few Jupiter like sized planets. So we're really looking like 20, 30 years later when we have the power for a telescope like LUVR, but maybe can get down to the size of these kind of intermediate size exoplanets, but not in the near future, okay? So the way I think of this problem, again, like I don't really know the solution, but I want to look at what is going on by maybe trying to find some inspiration from solar system planets. So I decided to look at, okay, so how about we look at Jupiter, which is kind of the edge case for like a very thick atmosphere and very deep surface case, versus Titan, which has a much shallower surface, because why not? Because I've been studying Titan for so many years. And I'm trying to find the differences between these two bodies. So what I found is that actually there are 2 atmospheric species that completely have different evolution in the atmosphere of these 2 planets. Both species actually, both planets both get destroyed constantly by UV photons to form photochemical products, simplified something like nitrogen or the hydrocarbons. But for Jupiter's case on the left, these photochemically formed species keep being transported to the deeper and hotter part of the atmosphere because there is one. And then because it's a hydrogen-rich atmosphere that is very hot, pressure is very high, these photochemically formed nitrogen hydrocarbons actually can be converted back to their parent species through thermochemistry. So that means the ammonia and methane are reformed in the deeper part of the atmosphere that can be further then transported back up into the atmosphere to replenish the destroyed ones. But in the end, we expect to see lots of ammonia and methane still for Jupiter's atmosphere. So that's how we think these 2 species operate on Jupiter. But for the case of Titan, because there's a shallow surface, so these species, after they're formed, they have nowhere to go. For nitrogen, it would just fill the whole atmosphere. And that's why Titan has a nitrogen-dominated atmosphere. And for the hydrocarbons, again, they have nowhere to go but to be deposited on the surface. That's why we're seeing lots of surface sediments that are organic rich. For example, the dunes have been studied forever. They're organics that cannot escape but be deposited on the surface. But this is really saying, okay, once you started this atmospheric reaction to destroy ammonia and methane, this keeps going, and this actually exhausts these atmospheric species quite quickly in terms of geologic time. And we really expect to see depleted amount of ammonia and methane in an atmosphere with a very shallow surface. So I was just wondering, okay, looking at the dichotomy between these 2 planets and the fate of these 2 species, can we maybe use the abundances of them to try to make some proxies to figure out the surface conditions for exoplanets? So 2 years ago, I did this for a planet that's kind of in between size. It's a little bigger than the optimal size we have for K218b. It's about 2.6 Earth radii and relatively lower temperature. So that's kind of ideal for this study. And we kind of implemented this using a photochemical model, implemented this idea. So what we did is basically we add surface at different levels and then figure out if there's a difference in the species abundance that we get after we evolve the planet atmosphere composition. So the thick gray line he's showing here is actually the abundances of ammonia and methane. But this is assuming when you have a very deep surface, okay, like Jupiter. And then once we add in like 100 bar surface for ammonia, as you can see, there's no difference, okay? And if we add a 10 bar surface, now you're starting to see, okay, ammonia abundance starts to drop. And if you add a 1 bar surface, it drops even further, okay? And for methane, if you put in 100 bar surface, okay, nothing changed, just like ammonia. And now if we put in a 10 bar surface, okay, this is different now, but methane 10 bar surface actually doesn't make its abundance decrease at all. It's not until we put in a 1 bar surface, so we start to see a decreased abundance of methane. So this really tells us, okay, this actually works. The idea we had for ammonia and methane kind of works, but there's something actually better than we thought, because we found more species that are sensitive to a surface condition. For example, we found stuff like HCN, some hydrocarbons, and CO and CO2. They're actually pretty sensitive as well. And it seems like there's some difference of sensitivity between the nitrogen and carbon species. So we're actually able to, that really allows us to not only be able to tell, okay, does this planet has a shallow surface or a deep surface, but we can maybe figure out the intermediate case. So that made us to make this flow chart out of this work. And the idea is we're going to hopefully have some JWST observations, which is actually upcoming for K218b. To be able to distinguish this, for example, K218b has a deep atmosphere, like a thick atmosphere and a deep surface, or a thin atmosphere and a shallow surface. And my student has been kind of keep doing this work. Ziyu Huang, he's a grad student at USC. He's actually going to do a postdoc in Boston University very soon. So moving to the East Coast. But he has been kind of looking at these behavioral planets, but towards the cooler side. So, for example, we've done the modeling for like a cold edge planet around 180 Kelvin. And this is really to try to understand, once you have water condensation, how does the surface sensitivity change? And what we found, it seems like with water condensation, it does change the response, especially for CO and CO2. So instead of getting increased abundance of CO and CO2 for the shallow surface case, we'll actually get less because of water condensation. But again, we'll keep doing this kind of work, and a previous undergraduate student at UC Santa Cruz have been generating transmission spectra for us. But basically, we're looking at these kind of opportunities to find surface level. And I would say ammonia seems to be the best species to look at. So there's a feature around 3 micron and a feature at 10 micron. And if we see a depletion of ammonia, that can tell us this planet might have a shallow-ish surface, so like less than 10 bar. This is for K218b. And there are lots of features we can look at in terms of methane, CO, CO2, water that can help us distinguish whether it's shallow surface or deep surface. And the better case is, well, there are more planets we seem to be able to do this kind of surface condition identification. So I would really say this is the opportunity that the James Webb Telescope provided us, the so-called super Earth opportunity. Even though we're not at the stage we're able to, see the composition of rocky worlds, or it's going to take many transits, lots of observational effort to be able to look at these tiny rocky worlds. But instead, we can go to these little bit more like larger radii, like a little bit hotter planets, and really to find, okay, are these super Earth planets possible to be like, the so-called rocky worlds, or potentially be habitable? So we have all these range of targets that are going to be observed by the guaranteed the GO and GTO and cycle 1 observation. I hope there are definitely going to be more from cycle 2, but there are 14 targets already that we can do from cycle 1 observations. And we've done K218b, and my students are actually working on this really interesting planet that's really ambiguous. We don't really know how thick the atmosphere is on the surface level for LHS 1140b, but there's all these other targets, so interesting telling. And we're hoping to provide some statistical information. For example, okay, if your planet radii is like less than 1.3 radii, you are more likely going to be a rocky world. But maybe it's above something, it's more going to be an intermediate sized planet, and something like that. But really, we have to do this for like enough samples, but there are a lot already in our current JWST samples. But yeah, I would like to then conclude my talk, and I hope you found the laboratory work we've been doing, this kind of collaborative way to measure the Titan hazes, really useful. Well, not only the Titan community, but people who study other planets. And I hope you think this super Earth opportunity is really like a golden period for like JWST to assess some of the habitability information, even before we're able to assess it for the smaller Earth-like exoplanets 20, 30 years later. And lastly, I hope you think the solar system planets are actually great inspiration points for exoplanet research. And I'll end my talk here and leave the final slide for any questions you might have. And that's it, Tim.
All right. Thank you so much for this very great talk. I give a round of applause for because it's always so disappointing when we only have the emoticons. Thank you so much. That was very exciting. Yeah. So yeah, I leave the slides up. Maybe this will be helpful. So I think we can go over immediately to the questions and just shortly, yeah, just raise your hand via the Zoom feature if you have a question, and at best unmute yourself and show your video when you ask a question. So do we already have a question now? Yes, very good, brave. Dennis, please let us know what.
Right. Do you hear me?
Can you
Yes.
it's a bit yeah.
A bit quiet. Hang on.
There.
About now? Yeah. Okay. Yeah, thanks for the great talk. It was really fascinating, all the work you're doing. So I had a question about sort of using Titan as an example for shallow atmospheres, and as you said, using the abundances of ammonia and methane to sort of estimate a possible surface pressure. How do you reconcile the relative abundance of methane on Titan with the idea of it being photochemically destroyed? And so there's, as you know, there's still this conundrum of why there's a lot of methane still there, and why is it not totally destroyed? So does it throw a spanner in your work in that regard?
That's a great question that I deliberately did not get to during my talk. So thank you for asking that. But yes, for Titan, we know that methane is not primordial because we have isotope measurement that tells us the methane is not primordial and it has a link to the interior. So the idea is we know the methane is probably coming from the interior. But this gives us a challenge because for these exoplanets, it could also outgas, right? In terms of methane or whatever these kind of species to kind of interfere with our surface identification framework. So we might be getting false positives or negatives of super Earths like planets versus not. And so this is something we've been doing. So my student Zhu has been testing for LHS, at least adding the biggest possible flux of methane and ammonia to the model, and then see if this affect our interpretation. And for at least for the planet we're doing, because it's much, much bigger and the flux, we're trying to use a really big flux. So it does bump up the abundance a little bit, but it's still quite low actually. But Titan is a much, much smaller body also. And it's a little bit colder. So the destroy, I would say, is actually more efficient for these a little bit higher temperature bodies, and also they're bigger planets. So it seems like it hasn't been a big problem, but I would say ammonia outgassing is really, so we really think ammonia is the best species to do this surface identification, because whatever flux we put in, ammonia abundance is mixing usual stays less than 1e10. But methane does bump up a little bit, yes. But thank you for the great question.
All right. Do we have any more questions? If not, in the meantime, I'll actually have a question. First of all, about the exoplanet work you've been doing on the surface levels. So there has been this follow-up working from your paper regarding water oceans, but this is more of a general question actually. So several species like nitrogen species and carbon species, they can be dissolved in liquids, be it water or be it magma or whatever, and it changes depending on redox state. So what I've been wondering is whether there's a potential that these signals can be false positives rather than being chemically related in the atmosphere from thermochemistry, somehow related to deeper interior liquid layers of the planets. Do you think we have a chance to disentangle liquid dissolution with different redox states from actual thermochemical like effects, or yeah?
Yeah, so that's a great question too. So magma, yeah, since this is discussion, so for the liquid, it's good, right? So if there's a liquid ocean, which means it probably has some sort of surface that could hold like a liquid, which is good. And it will just enhance the signal. So it will reduce even, with atmospheric chemistry, you get less ammonia, but then then you'll get even less because of the dissolution effect. So that's good in terms of like surface identification. For CO2. We didn't use CO2 actually in our identification framework because CO2 does it. So for the 1 bar surface, we see increased levels of CO2, but like you said, CO2 dissolves in the ocean. So that's why we use CO instead. So CO is like more stable, and we see an increased level of CO actually for the shallow, like 1 bar surface case. So that's kind of why we decided to use CO. But yes, it does cause an interference. And in terms of the magma thing, I feel like there's recently, I saw like AGU talk, they've done like some magma ocean related work. But yeah, like I don't know enough about like magma oceans to say. So if you have a magma ocean planet, then like how much stuff is gonna dissolve in the ocean that's gonna cause an interference. But yeah, like any other people, magma oceans, right?
Yeah, but I want to know your opinion. So
yeah. So I've seen like
Yeah.
a talk, but I think what they're been doing is a little bit different in our approach. But depending again on like the species the magma ocean can take in. So assuming if a magma ocean is probably quite deep surface, and if it takes in some species, yeah. But I have to look into that actually, because the other thing, like to me, is like I've been thinking of more like shallow, colder surfaces, and for the deep stuff, I'm just treating it all like it's like a Teflon-like surface. So for our current models, like all the deep cases, there's no interaction between the deep surface and the interior. But maybe that's something that's worth considering in the future, actually. Especially I know like there is this thing like magma ocean can actually last quite long for these like intermediate sized planets. That's kind of some of the modeling work have shown that.
Okay, thanks. Do we have any more questions?
I have a small question if nobody else has.
Yeah, please go ahead.
Okay, so this is just a question about your lab experience with Tholins. So when you compared results from different labs, did you look at the structure of Tholins and their, for example, fractal properties, or how long the chains are and stuff like that? Did that vary a lot?
We haven't looked at that, but that's our plan to look at their microscopic properties. But yeah,
Right.
We have lots of sample that to be measured. But currently it's just me in the lab, but I'm getting grad students finally. So yeah.
Sounds great.
All stuff on the list to be done. Yes.
Yeah, great. Good luck.
Yeah, thanks for the suggestion. Yes.
Okay, I have also one more question. We don't want to stretch it too long. There are no follow-up questions, but I have one more, which is a bit more philosophical, actually, in a sense. So you were motivating in the very beginning, right? You were motivating your work on Titan, with reducing chemistry, it potentially can contribute to the origins of life. But like when I hear prebiotic chemists talking, I hear that there's something like you can be too reducing, right? Too reducing atmospheres can also some are not productive, right? Or they produce chemical species that are not as essentially helpful in prebiotic reactive networks.
Mm-hmm.
So Titan is probably one of those worlds, right? So my question is, in a sense, when we study these tholins, or when you study these tholins, and when Dragonfly is visiting Titan, are we actually learning something about the origin of life, or are we learning about chemistry that is too reducing to be really the equivalent of the early Earth's chemical environment?
That's actually a great question that I feel like the Dragonfly team needs to do better in selling the mission. It's an astrobiology mission, believe it or not. It's not like a Titan Dune Explorer mission. So as you can see, the atmosphere is missing oxygen, right? There's nitrogen and methane. Water is too frozen to kind of release too low of a vapor pressure to include everything, be included in the chemistry. So the idea of the mission is that once you form these hydrocarbons, plus nitrile, CH molecules on the surface, the bedrock is actually not silicates, but water ice, okay? But if you have like an impact on the surface that can melt the water ice, and that tend to form like an impact melt for like a significant amount of period. So that means you're soaking these HCN molecules inside a liquid water pond for like maybe 100 years, something like that, if you get a big crater. Then that's where we introduce oxygen. And people have done this experiment. They basically throw Tholin in like a water, like ammonia kind of controlled like water solution in the freezer. And then they see like how the composition changes. So that's they call the hydrolysis experiment. And they actually found like stuff that like amino acid like material. So this is the Dragonfly mission is actually going towards the equator to assess, okay, during this impact melt period, how far does this kind of like hydrolysis went? And is there like how far did it go? Like what kind of molecules did it make? But that's where the oxygen was added for Titan's case, if that makes sense. But I would say like for a hotter planet, that water do not like condense out, like become ices, like frozen cold. We should be having some oxygen simultaneously with some reducing components in the atmosphere, I would say. But yes, that's how Dragonfly is still doing prebiotic chemistry. Yeah.
I understand.
So hopefully that's making more sense to you about why astrobiology is important, like it's a Dragonfly mission selling point.
Yeah, no, I didn't know that. Thank you.
Yeah.
Okay. Do we have any other questions? No, I don't think we do. So I think thank you again. Let's thank our speaker again for this great talk and discussion afterwards. We will have another discussion next month in the beginning of May given by Junko Renaga on early volatile evolution of terrestrial planets. So thank you again, Xinting, for being here. And I think we can close the session now and also close